Welcome back to the Deep Dive. Today we're strapping in and focusing our attention on what feels like the next great technological inflection point.
It really does.
We're trying to move past all the daily headlines, the latest qubit count from some lab, and instead point our compass squarely at the scientific horizon of quantum technology.
Yeah.
So we're focused not on what quantum computing is today, but where this whole field is heading over this really critical decade between, say, 2025 and 2035.
And that is the essential framing for this whole conversation. I mean, we've synthesized a stack of analysis that's focused specifically on the trajectory of maturity.
And you're calling this period the quantum horizon.
We are, the quantum horizon. And it's an essential distinction, because the real impact of quantum isn't going to be some single launch event. It's not like a rocket going up.
Oh, okay.
It's a cumulative, systemic ripple effect that will fundamentally reshape major societal pillars.
Okay, so when you say pillars, we're talking about...
We are talking about the acceleration of medicine, the complete transformation of global finance, optimizing these incredibly complex logistics networks, and, well, fundamentally altering global security structures.
And by extension, society itself.
By extension, society, exactly.
So our mission in this deep dive is a detailed but also accessible exploration of these trends, the predictions, the exciting breakthroughs, and I think crucially, some of the seriously unsettling possibilities that come with a technology this powerful.
Mm-hmm.
We want to provide you, the listener, with the roadmap that's being drawn by researchers and corporate giants and even governments right now, just so you're well informed about the imminent disruption this all promises.
Exactly. We're looking at the projected pathway of maturity. We're tracking the shift from the purely experimental, the stuff in the lab, to tangible, world-changing implementation.
And understanding that trajectory, it's not really optional for being prepared, is it?
Not at all. It is a necessity. Particularly because the lead time, the time it takes to deploy these things and to mitigate the risks in this field, it is extremely long.
Okay, let's unpack this then. Let's start with right now, the present moment. When we look at quantum computing in 2025, we have to be honest about the current reality.
Right.
We're still very much in the infancy stage.
Mm-hmm.
I mean, these machines get billed as these supercomputers, but they're not really ready to run classical computers out of business, not in a practical sense.
That is the critical baseline we have to establish. Right now, the hardware is characterized by an acronym you'll hear a lot, NISQ.
NISQ. Okay, what is that?
It stands for Noisy Intermediate Scale Quantum Computing. So what does that mean in practice? It means quantum computers are inherently noisy, they are incredibly error-prone, and no, they are not consistently ready to outperform our classical systems in, the vast majority of tasks we use computers for every single day.
Okay, let's dig into that word noisy. For someone who's not a physicist, what are the actual engineering challenges that make these systems so fragile? We hear about, these massive refrigerators and vacuums.
Yeah, and that's all part of it. It really boils down to two core battles: stability and quality. The systems are fragile because they rely on controlling these incredibly delicate quantum states, the qubits.
The qubits, right.
And the main challenge is something called coherence time.
Coherence time.
Which is basically how long can that fragile quantum state maintain its integrity before any kind of environmental disturbance, like a tiny temperature fluctuation or a stray electromagnetic field, causes the whole computation to decohere.
And just fall apart.
It just fails. And that is why you see this massive, intricate infrastructure built around these systems. You mentioned the refrigerators. A lot of them operate near absolute zero, just to minimize every last bit of that environmental interference and try to stabilize the state.
So we hear these big announcements from the major players. We've achieved a system with hundreds or even 1,000 qubits. But it sounds like that headline number doesn't really tell the whole story.
Not at all. The noise and the error mean that even with a huge number of physical qubits, the practical, useful compute time is highly, highly limited. It's absolutely a quality over quantity problem right now. And this is where we need to introduce a really crucial distinction.
Okay.
The distinction between physical qubits and logical qubits.
Physical versus logical.
Yes. To correct for all that inherent noise and the errors in the physical qubits, you have to use these really complex error correction code. And current estimates suggest you might need anywhere from, say, 100 to maybe even 1,000 of those really noisy physical qubits.
1,000.
1,000, just to create one usable, stable, error-corrected logical qubit.
Wow. Okay, so the useful capacity is just a tiny fraction of the raw count they announced.
A tiny fraction.
Precisely.
Ah.
That dramatically alters the timeline for when this stuff becomes useful in the real world. But, okay, despite all those limitations, the noise, the errors, the fragility, we have to highlight the undeniable progress.
Oh, absolutely.
It feels like quantum computing is moving away from being a purely theoretical concept in academia and into practical implementation. How are we measuring that shift?
I'd say we measure it by two big factors: investment and technological diversification.
Investment. Okay, that makes sense.
On the investment side, governments globally are recognizing the strategic importance here. They're pouring billions of dollars into this. I mean, the US, China, the EU, they're in a very serious technological race.
And the corporate side.
Well, you have the established tech giants like IBM and Google, and they're mostly pursuing superconducting systems. But then you have these dedicated quantum startups like IonQ, focusing on a totally different approach called trapped ion technology. And then others are exploring photonic systems or neutral atom systems.
Wait, let's pause right there for a second. For our listener, why are there so many different hardware types? And why does that matter so much right now?
It matters because no one has definitively won the hardware race yet. It's still wide open. You have these distinct competing modalities, and each one has its own pros and cons.
So what are the big ones? You mentioned superconducting.
Right. Superconducting circuits, that's the IBM and Google approach. They're very fast, which is great, but they require those incredibly low temperatures we talked about, almost absolute zero. Very complex, very expensive to run.
Okay. And the alternative? Trapped ions.
Trapped ions, that's what IonQ uses. They use electromagnetic fields to suspend individual ions in a vacuum. The benefit is they offer much higher quality, better coherence, but the downside is they tend to be slower to operate.
So it's a trade-off, speed versus stability.
It's a classic engineering trade-off. And then you have photonic systems, which try to use particles of light. Their big advantage is they can operate at room temperature, which would be a game changer. But scaling them up is a huge challenge.
So the fact that billions are being poured into all these different diverse approaches, it shows the market believes a solution is coming soon, but the actual path to that solution is still really uncertain.
Exactly. And these prototypes, which were once confined strictly to these, hyper-specialized research labs, they're now becoming functional, accessible computing platforms that people can start to use.
And that transition from a high-risk prototype to a commercial platform you can log into, that's a huge shift in technological maturity.
It is.
To put this current shaky experimental state in perspective for everyone, our sources use a really fantastic analogy.
Yes, the aviation analogy. I love this one. It paints the perfect picture of where we are right now.
And the analogy is that quantum computing today is remarkably similar to the early days of aviation. We're talking specifically about the 1910s.
The 1910s.
The 1910s. So
Yeah.
we're talking about biplanes, these flimsy aircraft made of wood and canvas.
Yeah.
Machines that were shaky, experimental, and certainly not reliable for mainstream transport.
Not at all.
You might see a demonstration at a county fair, but if you tried to rely on a flight across the country in, say, 1915, people would rightly look at you like you were crazy.
Absolutely. The first flights were incredibly dangerous.
Right.
They were limited in utility. The engineering was totally bespoke, one-off stuff. And the challenges were so foundational. How do you build stable wings? How do you create reliable engines? How do you even navigate?
Right.
Yet, despite all those inherent risks and the limitations, everyone involved, the engineers, the military strategists, the futurists, they knew fundamentally that this technology would eventually change the world.
They could see the horizon.
They knew aviation would shrink the globe. It would revolutionize travel and logistics and warfare. The potential was seen as inevitable, even if the current state was highly restrictive.
And the parallels here run really deep. Just as governments and wealthy patrons funded those shaky biplanes for a strategic advantage, for military reconnaissance, modern governments are funding these billion-dollar quantum initiatives today for the exact same reasons. And the skepticism that existed back then, that planes would only ever be these little novelties, it's the same kind of skepticism we sometimes see now about quantum's long-term utility.
It's the same cycle. It's an exciting but still nascent technological moment. It's defined by massive investment and this huge struggle to achieve basic engineering stability.
So the great technological leap was the transition from those flimsy, dangerous biplanes to, the reliable mass-produced airliners like the DC-3 in the 30s.
Exactly.
And that transition is what we're going to track in the next segments. The shift from the noisy, physical qubit systems of today to the stable, logical qubit platforms of tomorrow.
That's the journey.
Okay, so if 2025 is the experimental biplane that's struggling with high winds, let's look at the immediate horizon. Let's look at the path up to 2030. What does moving past that biplane era specifically mean in terms of engineering milestones? Where's the first measurable leap?
The measurable leap is defined by two words: stability and utility. Over the next 5 years, we can expect steady, measurable progress. But crucially, the focus of the entire industry shifts from just getting more qubits.
Right, away from the headline number.
Exactly.
Yeah.
And toward achieving higher fidelity and much better error correction. We are moving toward systems where, even if the total qubit count isn't astronomical, the usable logical qubit count starts to creep up in a meaningful way.
Reduced noise and better stability. So those are the foundational engineering battles that will determine whether the system is reliable enough to run complex, repeatable calculations.
Yeah.
This is about making the planes safer and reliable enough for, say, specialized industrial routes, right? Not for passengers yet, but for high-value cargo.
Precisely. And this intense focus on engineering refinement and fault tolerance is what bridges the gap between the specialized research lab and initial industrial application. As the hardware stabilizes and those error rates drop, the computers become robust enough to start tackling meaningful, specialized problems. Problems that classical computers simply cannot handle efficiently due to time or resource limitations.
And this leads us directly to the first wave of industry adoption. So it's not going to be some universal switch that flips overnight.
No, not at all.
So which industries will be the first beneficiaries? And what are those specific niche problems that quantum is set to tackle first?
The initial adoption will be highly concentrated in areas defined by complex combinatorial optimization and simulation.
Combinatorial optimization. Break that down for us.
It just means solving problems that have an astronomically large number of potential solutions or combinations. And the systems we'll see deployed by 2030 are best at exactly that.
So a concrete example?
The first major industry example is pharmaceuticals and drug discovery.
This seems incredibly complex and messy. How exactly does quantum simulation, given all the limitations we just talked about, actually begin to help a pharmaceutical company?
It targets a very specific and fundamental bottleneck in their process. Classical computers, even supercomputers, struggle immensely when they're trying to accurately simulate the interactions of complex molecules.
All right.
So when you're trying to find a new drug candidate, researchers need to determine the optimal configuration of all its atoms. It's called the molecule's minimum energy state. And classical systems, they have to rely heavily on approximations and use these really computationally expensive methods like Monte Carlo simulations to even get close.
And why does that get so hard for classical systems as the molecules get bigger and more complex?
It's because the complexity scales exponentially. For every atom you add, the number of possible quantum states you have to model just explodes. A quantum computer, on the other hand, operates based on the same principles of quantum physics. It can natively handle these simulations.
So it's speaking the same language as the molecule.
That's a great way to put it. It allows pharmaceutical companies to model new drugs and potential treatments at a foundational molecular level. Things like predicting how a candidate molecule will bind to a target protein in the body.
So it significantly accelerates the very early stages of discovery, before you even have to start doing costly physical testing in a lab.
Exactly. It doesn't replace the entire lab, not by a long shot, but it dramatically speeds up the most time-consuming and expensive step, identifying the most promising candidates to pursue out of millions of possibilities.
And that transition from, say, months of approximation to potentially days of high-fidelity simulation, that's a huge potential breakthrough for human health and just the speed of innovation.
Huge.
What's the other major niche industry that's expected to see adoption during this near-horizon period?
It would be logistics and complex supply chain management. Think about massive global supply chains, complex routing challenges, managing fleets of vehicles or drones, or even global ship reroutes. These are all at their core problems of optimization.
I can absolutely see how that becomes exponentially complex. I mean, if you have 10,000 delivery points in a city and you have to account for traffic and variable fuel costs and load limits on the trucks and scheduling constraints in real time, the number of possible routes is just far too large for a classical computer to check every single possibility.
That's precisely right. Classical algorithms have to rely on heuristics.
Heuristics meaning shortcuts.
Shortcuts, exactly. They provide a good answer, but usually not the absolute optimal answer. Quantum algorithms, however, are uniquely suited for these problems. They often use frameworks known as QUIA,
QUBO, what's that?
It stands for Quadratic Unconstrained Binary Optimization. It's a bit of a mouthful, but it's a way you can map all those complex interconnected constraints, the traffic, the delivery windows, the truck capacity, onto the quantum system itself.
So the quantum computer explores that vast landscape of possibilities much more effectively than a current supercomputer that's just relying on approximations.
Much more effectively.
So what's the real world benefit here? Are we talking about a 1% improvement in optimization?
You say just 1%, but even a 1% improvement in efficiency across a massive global logistics network like Amazon's or FedEx's can translate into hundreds of millions, maybe billions of dollars in fuel savings.
Right. And a reduced carbon footprint, faster delivery times.
Exactly. So by 2030, these hardware improvements will translate directly into specialized quantum systems, offering clear, demonstrable competitive advantages in these focused areas.
So the key prediction for this new horizon, 2025 to 2030, is that quantum computing successfully moves from being purely a research project into these specialized industries where it can offer a concrete competitive edge.
That's the milestone.
So the analogy shifts then. We're moving from the Wright brothers biplane to perhaps the first functional, if specialized, cargo plane, something that opens up a profitable niche route that was previously impossible.
That's a perfect way to frame it. It's the tipping point from academic curiosity to a specialized industrial tool, proving that technology works outside of the lab.
Okay, so moving beyond that initial niche adoption phase of 2030, we now look at the core of the quantum horizon, the period between 2030 and 2035. And this period is defined by a massive, all-encompassing milestone, the achievement of quantum advantage.
This is the moment. This is when the trajectory fundamentally changes and the world really begins to feel the systemic impact.
Define quantum advantage for us. How is it different from just, being a bit faster on certain problems?
It's a huge difference. Quantum advantage is not just about being faster sometimes. It's the key milestone where quantum computers consistently, robustly, and repeatedly outperform classical ones in meaningful real-world tasks. Tasks that fundamentally impact revenue or health or national security.
Okay.
This is the moment the floodgates open for transformation across entire economies.
The floodgates opening. That suggests a really rapid acceleration of impact across many sectors, moving well beyond those specialized niches we just discussed.
It does.
So once that advantage is achieved, and that means we have enough stable, logical qubits to do real work, how does the economic transformation begin to unfold?
It stops being about incrementally better computing, and it starts becoming about unlocking entirely new capabilities. The impact goes far deeper than just running current calculations faster. It enables solutions to problems that were previously completely intractable.
And that's what reshapes market efficiency and scientific discovery.
Completely.
Okay, so let's start with finance, an industry where tiny advantages can equate to massive profits. Our sources really emphasize a revolution in this sector. How does quantum advantage fundamentally change how financial markets operate?
Well, the complexity of global financial markets, especially when you get into derivatives and correlated assets, is just staggering. When quantum systems achieve advantage, they will drastically change optimization and risk modeling. For example, current systems struggle to perform true high-fidelity risk evaluations across highly complex portfolios in real time. They have to rely on sampling and approximations. They just can't see the whole picture at once.
But quantum systems would change that.
Absolutely. Imagine quantum algorithms that are capable of analyzing and optimizing investment portfolios across thousands of correlated variables simultaneously. This just far exceeds the capacity of our current statistical models.
Okay, give us another example.
Derivative pricing. It involves evaluating options based on all these fluctuating future paths. A quantum algorithm could process calculations almost instantaneously that currently require hours or even days of massive classical compute time on a supercomputer.
So that means predicting market trends becomes much more sophisticated. It could allow for entirely new strategies that classical systems couldn't even conceptualize.
Right. We're talking about moving from statistical averages to near-perfect optimization across these incredibly complex, noisy datasets.
What about risk?
That's the other huge piece. It's about complex risk modeling. Understanding interconnected systemic risks in real time. Moving beyond traditional models like value at risk, or VAR, which often fails spectacularly during so-called black swan events.
Like the 2008 financial crisis.
Exactly. With quantum capabilities, institutions gain the ability to predict market trends with a level of accuracy and nuance that current systems simply cannot achieve. This isn't just an incremental improvement. This is fundamentally changing the mechanisms of high-frequency trading, credit scoring, portfolio management.
The sophistication of financial products will just jump exponentially.
It will. But that sophistication comes with its own set of new risks, of course.
Of course. So beyond finance, the other area that's poised for an absolute explosion of innovation is material science. Why is quantum computing so uniquely suited to driving breakthroughs here? And why does this matter so much for the global economy?
Material science is, at its heart, inherently quantum mechanical. When you're trying to design a new material, you are observing and manipulating the interactions between atoms and molecules.
It's just like in drug discovery.
Exactly the same principle. Simulating these interactions classically is computationally intractable. Quantum simulation, however, enables the efficient design of breakthrough materials with properties that were previously unattainable.
So give us some concrete, world-changing examples of what these breakthrough materials could be.
Okay, we're talking about next-generation technologies that could solve some of our biggest global challenges. Things that are crucial for the energy transition.
For example?
For instance, designing new, highly efficient catalysts for industrial processes. Maybe even catalysts that could dramatically improve carbon capture efficiency, pulling CO2 out of the atmosphere.
Wow.
We're also talking about designing new battery cathodes and electrolytes. Batteries that are safer, charge much faster, and hold far more energy. That's critical for both electric vehicles and for grid-scale energy storage.
That would be a game changer.
But perhaps the most revolutionary concept, the holy grail, really, is the design of high-temperature superconductors.
Explain that. Current superconductors have to be cooled down to crazy low temperatures, right?
Right. Near absolute zero, using liquid helium. It makes them incredibly expensive and impractical for widespread use. But if quantum simulation can help us design a material that superconducts at or near room temperature,
that would change everything.
it would revolutionize energy transmission. It would eliminate energy loss across power grids globally. Billions of dollars saved, a massive reduction in energy needs.
So that kind of materials science explosion, it's not just a side effect, it's a foundational transformation of industrial capability. It could fundamentally reshape the geopolitical balance by creating new energy dependencies and opportunities.
Exactly. I mean, think about it. The country or the corporation that designs the first efficient room temperature superconductor essentially controls the future of energy infrastructure.
That capability shifts the global economy away from, say, who has the most oil, and toward who has the most intellectual property and simulation power. So by 2035, this isn't some experimental technology sitting in a dark, cold lab anymore. The expectation is that this level of quantum solution will be woven into the fabric of daily industry. It becomes a critical component of mainstream workflow.
Correct. By 2035, industries won't just be experimenting with quantum solutions. They will begin integrating these quantum systems and algorithms into their mainstream workflows and their core operational infrastructure.
So a materials lab using a quantum simulator to test a new alloy design becomes standard practice.
Standard practice.
Yeah.
Or a major bank using quantum modeling for its daily risk assessment. The technology moves from the periphery to the central nervous system of global commerce. And that shift represents the true culmination of the quantum horizon.
As exhilarating as these scientific and economic breakthroughs sound, it is. It's absolutely crucial to recognize that massive technological power always brings commensurate risks. The very power that enables breakthroughs in material science, the ability to model subatomic physics, is the same power that simultaneously unleashes the ability to break classical cryptography. So we need to flip the coin now and discuss the challenges. And let's start with the most alarming one, the encryption threat.
This is often dubbed the Q-Day threat, and it is, without a doubt, the biggest risk associated with the quantum horizon. This is the potential for these powerful machines to break today's standard public key encryption protocols.
And this isn't just theoretical fear-mongering. This is a calculated vulnerability based on mathematics.
It is. Specifically, an algorithm called Shor's algorithm.
Okay, for our listener, we really need to pause and explain the underlying mechanism here. Current encryption, like RSA, it works because of computational difficulty, right? Why is factoring large numbers the cornerstone of our current security?
Well, our current security relies on a simple fact. While it's very easy for a computer to multiply two very large prime numbers together,
Okay.
it is computationally impossible for a classical computer to work backward, to take that big resulting number and find the two original prime numbers you started with.
Not in any reasonable amount of time anyway.
Exactly. Even the fastest supercomputer in the world would take centuries, maybe longer. It essentially renders the task secure against any kind of brute force attack.
And how does Shor's algorithm fundamentally alter this?
Shor's algorithm was designed specifically for a fault-tolerant quantum computer, and it exports the principles of quantum mechanics, specifically superposition and entanglement, to find those prime factors exponentially faster.
So it's not just a faster brute force attack. It's not just trying every number more quickly.
No, it's a completely different mathematical approach.
Yeah.
It changes the problem from taking centuries to taking minutes or hours once that fault-tolerant hardware is built.
That is a profound technical threat. What is the scope of this threat? Which major global systems are immediately vulnerable when or if Q-Day arrives?
The vulnerability extends across virtually all digital communications and secure transactions that are based on current protocols like RSA and elliptic curve cryptography, or ECC.
Pretty much everything.
Pretty much everything. It threatens global internet security, as most of the secure connections on websites use this type of encryption. More specifically, it poses a direct and immediate existential threat to banking systems, financial transfers, secure governmental communications, classified data storage.
And crucially, this threat extends deeply into the world of decentralized systems, which our sources specifically highlight. I think a lot of people assume that blockchain is intrinsically safe.
And that assumption is very dangerous. Blockchain technology, which relies fundamentally on cryptographic security and digital signatures to verify ownership and transactions, it's squarely in the crosshairs.
So what's the key vulnerability there? Is it the ledger itself?
It's not the ledger, not directly. The key vulnerability is the digital signature that's created using algorithms like ECDSA, the elliptic curve digital signature algorithm.
So if I understand correctly, the quantum computer doesn't need to rewrite the entire history of the blockchain. It just needs to be able to forge my signature.
Exactly that. When you spend cryptocurrency, you are essentially signing that transaction with your private key. If a quantum computer can run Shor's algorithm on your public key, which is visible to everyone, it can derive your private key.
And then an attacker can forge your signature and drain your wallet.
While the specifics of how quantum power might affect different blockchain structures can vary, the ability to break that cryptographic key fundamentally undermines the entire trust framework upon which these distributed ledgers are built. It's a massive, time-sensitive vulnerability.
There's also this horrifying strategy known as harvest now, decrypt later. What does that entail, and why does it make the threat immediate, even if we don't have these fault-tolerant quantum computers today?
Harvest now, decrypt later is the strategy where malicious actors, we're often talking state-level actors here, are currently intercepting and storing vast quantities of today's encrypted data.
So they're just vacuuming it all up.
They're vacuuming it all up and putting it in storage. They understand that while they cannot break the encryption now, they will be able to do so retroactively once a sufficiently powerful quantum computer exists in, say, 2030 or 2035.
So, highly sensitive data trade secrets, classified documents, patient records, financial data that needs to remain secure for decades is already compromised. We just don't know it yet.
It's already compromised. The breach won't be realized for another 5 to 10 years, but the theft has already happened.
So if that's the technical and security risk, let's shift to the societal and ethical challenges. If quantum power is concentrated in just a few hands, what does that do to global stability?
This is a geopolitical and ethical challenge of the highest order. If quantum power is concentrated only in the hands of a few extremely wealthy corporations, or critically in the hands of a few dominant global governments, primarily the US, China, and the EU, it creates an enormous risk of global dominance. This is the specter of a quantum Cold War.
Define that quantum Cold War dynamic for us. What does a lead in quantum supremacy actually afford a nation, beyond just faster research?
A quantum lead offers unprecedented advantages in intelligence gathering, surveillance, and industrial dominance. The country or company that achieves quantum supremacy first will gain the unilateral ability to break their competitors' encryption,
giving them a persistent and undetectable advantage in military and commercial espionage.
Exactly. And furthermore, they would control the underlying infrastructure of all future innovation, designing all the best new materials, optimizing all the global logistics, modeling every major financial market.
So the differential in capability is so vast, it just risks widening the existing inequality between nations and within societies.
It's profound. The concentration of this power creates a profound instability, which makes international cooperation and ethical guardrails absolutely necessary if we want to maintain a stable global environment.
And finally, there's the immediate challenge of governance itself. I mean, we are moving into a technological landscape that is changing much faster than policy typically moves.
There is a significant governance vacuum right now. Quantum technology is advancing so rapidly, but the ethical frameworks, the regulatory standards, and the international treaties that we need to manage a technology this powerful are lagging severely.
So we risk widespread disruption and potential misuse that could destabilize global systems before we even fully realize the technology's benefits.
We must achieve governance before dominance is established. The window to do that is closing.
The risks are profound, particularly that cryptographic vulnerability, which affects every secure system on Earth. So what is the necessary technical response? How are the world's most critical systems being prepared for the quantum computing era?
The primary and most urgent technical response is the migration to post-quantum cryptography, or PQC.
PQC.
Right. This is the necessary preparation required to secure our digital systems against a future quantum attack. The focus is on developing new, quantum-resistant cryptographic algorithms that are mathematically resilient to quantum attacks, even by a powerful, fault-tolerant quantum computer.
And this is not just a theoretical concept being discussed in university labs. This is a massive, multi-year international standardization effort.
It is, and it's being led by key organizations. The National Institute of Standards and Technology, or NIST, in the U.S. is playing a vital global role here.
What are they doing?
They launched a rigorous, multi-year global competition to evaluate and select the best quantum-resistant algorithms. It's essentially a cryptographic bake-off.
A bake-off, I like that.
Yeah, you have thousands of submissions from cryptographers all over the world, and they are rigorously tested against both classical attacks and theoretical quantum attacks to find any weakness.
And what types of algorithms are winning or leading in this competition? What is the listener likely to start hearing about when PQC becomes standardized?
Well, the winning candidates, which include algorithms with names like Crystal's Kyber and Crystal's Dilithium, are largely based on something called lattice-based cryptography.
Okay, that sounds complex. What is that in simple terms?
In a nutshell, it's a fundamentally different mathematical problem than factoring large primes. It relies instead on these very complex, multi-dimensional geometric problems, finding the shortest point in a vast, complex grid or lattice. And that problem is believed to be computationally difficult, even for a quantum computer.
So we're just swapping one hard math problem for another, even a harder one.
That's the essence of cryptography, yes. And this standardization is critical because it gives hardware manufacturers, software developers, and yes, blockchain projects a unified target to implement.
And the migration has to begin now.
It has to begin now, because replacing our vast global encryption infrastructure, from routers and servers to personal devices and data centers, it's a project of unprecedented complexity and duration. We're talking about a decade-long migration effort that has to start well before the threat is fully mature.
Okay, so moving from the technical to the strategic, let's discuss quantum readiness for industries that aren't pure tech. Our sources draw a really compelling parallel to a massive technological shift we've already experienced.
They do. The parallel drawn is to the preparation that was required for the widespread adoption of the internet back in the 1990s.
Oh, okay.
Just as companies decades ago had to fundamentally rethink their business models, their security infrastructure, and their operations to accommodate the internet, industries must now prepare for quantum disruption.
And this isn't solely about implementing PQC. It's about thinking strategically about how quantum-enabled optimization or simulation will affect their competitive landscape.
Exactly. A CEO or an industry leader should be assessing where quantum solutions will replace their current classical bottlenecks. For example, in logistics or materials design or financial modeling, and then they need to proactively build the expertise to integrate those solutions.
So they need strategic foresight spanning 5 to 10 years, identifying potential quantum competitors, assessing where their current business logic, which is based on the limits of classical computation, will suddenly just become outdated.
Precisely. It requires pilot projects, dedicated quantum teams, and a clear roadmap for integrating these tools into core operations, long before their rivals gain that strategic advantage.
That sounds like a massive organizational challenge, and you absolutely can't implement this kind of readiness without the right people.
And that brings us to the crucial need for education and workforce development. It's a challenge that's often overlooked in this rush for hardware supremacy.
How bad is the gap?
The current knowledge base for quantum computing is concentrated within a very, very small, specialized group of physicists and computer scientists.
And we're moving toward a future where we're going to need thousands, if not millions, of people who can code in quantum languages, who can manage quantum clouds, who can design quantum algorithms for specific business problems.
Exactly. We face a significant academic pipeline problem. There's a huge shortage of quantum-ready programmers and engineers. We need to build a workforce that understands quantum basics, and we need to move this knowledge beyond a small group of physicists.
So what does that look like?
It requires a massive expansion of educational programs, interdisciplinary degrees that combine physics, computer science, and high-level math. We need to democratize access through things like quantum boot camps, online courses, and even integrating it into community college curricula.
Because if we don't build the human infrastructure, the machines themselves will remain locked behind this niche wall, accessible only to an elite few.
That's the risk.
And this workforce issue connects directly back to the larger societal implications we touched on earlier, particularly the ethical and geopolitical challenges of concentrated power.
It does. We have to prioritize the development of ethical frameworks right alongside the technological development. One key area is mitigating that geopolitical tension inherent in the race for supremacy.
So more international dialogue.
Essential. International dialogue is essential to prevent a runaway quantum arms race and to ensure some kind of level playing field for development and access. We need collaboration mechanisms that minimize the instability caused by highly asymmetrical technological capability.
And finally, tackling that inequality issue, the importance of access.
The importance of democratizing this technology cannot be overstated. I mean, if quantum capability remains concentrated only among the wealthiest nations or corporations, it risks widening the existing technological and economic inequality. It would further disadvantage developing economies and smaller players.
So you need policy.
You need policy. Ethical guidelines must mandate transparency, collaboration, and mechanisms to ensure broader access to the tools that will shape the next century of innovation. This requires intent, not just technical development, to ensure that the massive benefits of the quantum horizon are shared rather than monopolized.
So this deep dive into the quantum horizon reveals a period of just intense, rapid transformation ahead of us. We've charted the course from these shaky experimental systems struggling with coherence time in 2025.
The biplanes.
The biplanes. Through the specialized industrial adoption phase, those niche breakthroughs in logistics and drug discovery by 2030, and into the widespread economic revolution promised by quantum advantage in 2035.
The synthesis of our sources is clear. The next decade offers immense opportunities for breakthroughs in medicine, finance, and materials science. But it also carries major, undeniable systemic risks.
Particularly concerning global security and that vulnerability from cryptographic threats and geopolitical competition.
Right. The quantum horizon is significantly closer and more tangible than many people realize. This is no longer science fiction. It is an engineering reality that's on an aggressive timeline.
So whether you are in finance or logistics, security, or you're just keenly interested in the future of technology, now is the time to shift your focus. Don't wait for the mainstream headlines about quantum advantage. You need to be thinking about PQC migration and strategic quantum readiness today.
Our call to action for you, the listener, is to pay attention now. Stay rigorously informed about the PQC migration, because regardless of your industry, if you rely on internet security, this affects you and your long-term data security.
You need to support the development of robust ethical standards.
Yes, and most importantly, push for the rapid assessment and implementation of quantum-safe systems within your own organizations and communities.
And here is a provocative closing thought to leave you with, one that builds on the incredible speed of this trajectory. What unforeseen social or economic transformation will emerge when classical computers, the workhorses of our current digital economy, the foundation of every financial model and supply chain optimization, become, by definition, the performance bottleneck in every single major industry. When the fundamental limitations of classical physics dictate a slower, less optimal outcome in every sector, from global logistics to drug discovery, how quickly does the world reorganize itself around quantum speed? That profound and mandatory shift will define the next generation.